We will be starting in 5 minutes. I think we can start now. Um, I hope you are able to see my screen. Um, Thank you everyone for joining today. Good afternoon. And the thing that we want to discuss today first is we want to first introduce graphical models, the motivation behind it, and a little bit of Bayesian networks in this lecture. And before we start, we I also want to recap what we discussed yesterday. We discussed on regularization in and also ridge regression versus lasso regression. And lastly, we touched upon bias versus variance trade-off. And I think at the last part we sort of rushed a bit in the derivation part and all. So what I'm planning is for the first half of this lecture, we would be covering graphical models first, and then in the remaining 15-30 minutes, the end of the lecture, we can come back to bias variance trade-off lecture and sort of go through the derivation. So I have some slides for it. So I think I would be following from that slides instead of going through my handwritten notes. So that's our plan, and I think um, I we can start with the lecture on graphical models first, and yeah. So I think from for the last few weeks we had been discussing sort of setting up a background in terms of foundational machine learning concepts like logistic regression and linear regression. So we haven't covered logistic regression, but we have covered linear regression and things like maximum likelihood estimate and all those. And that sort of acts as a background setting, sort of to go into much more advanced portions in machine learning like graphical models. So just first start with the thing. So this slide is a little bit based upon some other professors at other and like researchers at other universities also. So I have just borrowed some images and all, and this showcase first. So I will start with the motivation first, in terms of, let me go full screen. So, why do we need graphical models? So, I'll be discussing what is graphical models, but what is the use case for this? So, if you probably know this thing about ACM Turing Award, which is one of the Nobel prizes, like the Nobel Prize for CS, computer science. And the one renowned researcher called Julia Pearl, who works primarily on causal reasoning and probabilistic graphical models. They are He is one of the pioneers in graphical model research and like the setting up the path for it. And I would highly recommend you to sort of go to this web page and sort of read through about like his work and all. And that sort of creates a new avenue in the field of machine learning, and that has a wide range of applications in many areas, starting from computer vision to natural language text generation and all, and also in recent language modeling. Any questions you have? Okay. So, what is graphical models about in terms of we want to make global predictions from local observations. So what do we mean by that? So let's say I from local observations basically means like, let's say I have an image of or in case of text, for example, in case of NLP applications, I have a text of say a sentence like, "Hi, today is going to rain" or something, and now you want to complete the sentence with some other words, and you can only probably predict locally like what is the next word after this sentence possibly, but can you also predict like what is the n plus 58th word, like what is the 50th word after ending of this sentence? So that's like global predictions, and it's broadly called inference in probabilistic inference or inference simple in a simple term. And the other concept is learning. So you have large quantities of data, just like what we saw in linear regression and all. You want to learn such models. And so there are two aspects: one is inference and one is learning, and we would be covering both of them as part of this lecture series. So one motivation is, in the case of like medical diagnosis, like you have some fact previous history of medical illness or some symptoms, and you also have test results. The thing that you want to check is what is the underlying disease, or if you give a treatment, like what is the treatment outcomes do you get. So treatment outcomes are actually observations in this case. And my global prediction would be, so local observations would be treatment outcomes, and my global predictions would be something like what is the underlying disease. Because treatment outcome, there might be multiple possible treatments. For example, if you have something related to your heart, like some blood systolic pressure or something like that, it may not be related to like heart attack or angina or something like that, but it can closely predict something locally. Like it can say like, your if your systolic pressure is high, then this and that can happen. But it can't predict globally in terms of like that in the following months or something you are going to have a angina attack or a heart attack, something like that. So that's the um, case of inference. Like how do we infer, based upon my current observations, how can I infer like global predictions. So the other example is in image segmentation. So for computer vision tasks and all. So let's say you have millions of pixels or color features. For example, you have an image like this, and you want to segregate that into different. You want to assign labels to the different objects here. So the cow has a label as foreground. The background building has a label BLDG, or short for building, and you have sky as a label for grass also. So how can you assign these labels, and since you have millions of pixels, because if you zoom in into this image, there are millions of pixels for this thing, and each of the pixel can have varying um, like differences in colors or features. So but you group all of those, like you group all the grass features or the grass colors into one corresponding label called grass. For the building, you group all of the pixels there into the building label. How do you do this? So this is where the graphical models come into picture. And so both of these two problems that I discussed, like both of these two problems have this thing in common. So one of the main issue is that both of them has many variables. One is in case of medical diagnosis, um, many variables are basically many symptoms, for example, or there are you do a lot of lab tests and lot of treatments, and you get different outcomes for it. And so there are many variables there, and you want to sort of see like how those variables are interconnected. Similarly, for the image segmentation part also, variables are the pixel. um, uh, there are millions of pixels, so there are millions of variables, and you want to know how all those are interconnected. And lastly, the main thing is, you are not certain like what is the correct answer. In case of medical diagnosis, you are not certain what is the underlying disease. Just you can just infer from different lab tests and all. um, there might not be, you might not get some patterns in the medical lab test and all, and you can't infer at those points. Similarly for image segmentation also and other applications. So graphical models actually provide a framework for in order to address this kind of problems where you have many variables, and you kind of have an uncertainty about the correct answer. So, um, firstly, graphical models is basically a model, which is like a declarative representation. And so you need data, obviously, and you need also some domain expertise, like domain knowledge. For example, in the case of medical diagnosis part, domain expert would be your doctors, and data would be like past patient like records, history of like symptoms and all. And your model would try to devise an algorithm to sort of uh, provide you like correct treatments. Like if you take this treatment, should be, you should get better, your outcomes should, like your symptoms should like get better if you take this treatment. So you need to predict correct algorithm, correct predictions for it, and the model actually devises different algorithms for that. So on a high level, you can think of probabilistic graphical models in that sense. We would be coming into the notion of graphs here, because the word graphical models has this word graph in it. And in the later stages of the slides, we would be seeing what do we mean by graphs here. So firstly, why is it probabilistic? Because it's to model the uncertainty. Obviously, I'm not sure about what's the disease, or the what's the sort of, in case of human segmentation, what's the label of the particular region of interest. And so uncertainty can be due to many things. Like one is partial knowledge of the state of the world, like, and also in case of, if you have noisy observations where you have error in the treatment. For example, in medical diagnosis, if you do lab test, you can have noise in the observations, noise in the lab test also. That means if you do blood test, for example, it might happen like your sugar levels may be um, slightly mismatched due to other different phenomena, like noisy observations are during the reading phase and all. Similarly, there are other cases, like one is phenomena that are not observed by the model, and also some level of stochasticity also, like randomness, that can actually create this sort of uncertainty. So what does probability theory as a whole provide? So we, in our lecture one, I think we did a very like short sort of crash course on like probability basics and all. And here, like, we would be heavily using those. So as we saw at that time also, like probability theory provides a, like a sort of standalone representation with clear semantics, because you have semantics like probability of an event, probability of an event given another event, and all those. And you also have reasoning patterns like conditioning, as I said, like using Bayes theorem and all. Like given an event, what is the probability of the other event happening. So conditioning and decision making, all these reasoning patterns is given by probability theory. The other part is also learning methods also. In linear regression, for example, the lecture we saw, there was also, we introduced a probabilistic representation of linear regression at that time. And that actually sort of helped us gain a different perspective on how linear regression occurs, like how the optimal weight values comes out to be the exact L2 loss, minimizing the exact L2 loss. So those kind of things is a is what probability theory would be providing us uh, for this sort of section of graphical models. And now I come to why graphical. So it's an intersection of ideas from both the probability theory field and the computer science field to. So graphs are basically like you have nodes in a graph, and you have those nodes connected via edges, and those nodes actually represent the large number of variables. So each node in the graph is actually a variable, and the edge would actually mean the relationship between any two variables. So for example, if I give you an application example, in case of the medical diagnosis part itself, um, there might be like things like, let's say, you do two tests. One is lab test on your blood test, and one is and you get a sort of observation that your lipid profile and all are high, like liver test, I think blood test provides. So in liver test, for example, your something is abnormal, and you also do another test on for your liver also, like a ultrasound or something like that, and there also you found something abnormal. And now these things are correlated because there is something um, happening in your liver, and that's why your ultrasound observation is giving you an abnormal sort of result. Also, your blood test will also give you an abnormal result. So these two observations are actually nodes in your graph, and the edge between them is actually a correlation between those. That's how we sort of like translate this sort of like the treatment observation kind of scenario into a graphical structure. So in the case of, as I said, like in the case of medical diagnosis, your variables would be like symptoms. Also, symptoms can be also your variables. Your predisposing factors can be also your variables. Test results, as I mentioned, can also be your variables. And in case of image segmentation, the um, pixel features like colors or features or the pixel itself can be act as my variables and also the nodes in the graph. So we want to my our goal is actually to capture the uncertainty through the joint distribution. So let's say each of the pixel I denote it as y1 y2 up till yn. So let's say entire image consists of n pixels, and each of them is indicated as y1 to a yn. And now what I want to do is I want to capture the joint distribution probability of y1 up till yn, and that's my uncertainty. And before we head on too much into more details, I just want to give you a overview of like what our upcoming lectures would include. Some parts we are not that in diving deep into it. Things like I think the smaller nodes actually are we are not going too much deep into it. But things like graphical models broadly can be divided into three parts. One is directed graphs, chain graphs, and undirected graphs. And chain graphs actually, why there is a connection between undirected and chain is because um, chain graph is actually a special case of an undirected graph. It's also a special case of a directed graph. What do I mean by chain graph? Chain graph is basically like you have nodes lying in a chain and you just have edges connected between them. That's a chain graph. So this thing is a chain graph. For example, Markov network, uh, input dependent, and CRF is a chain graph. So undirected graph also can be divided into two parts. One is Markov, three parts here. One is Markov network, click graphs, and factor graphs. We'll be discussing as lecture progresses on each of this. For the case of directed graphs, we also have Bayesian networks, and directed factor graph. And under Bayesian networks, also we have things like Markov chains, hidden Markov models, and all. So that's the sort of hierarchical structure. Um, before we head on, like, is there any specific questions you have? Sort of, please let me know.
One question I have was in one of your earlier slides, you are saying that you are encapsulating the domain expert. Uh,
Yeah.
is it done through artificial intelligence in terms of rules, or is there a different method
Oh,
to it?
I think it depends upon the application. I mean, how you devise it. Like it's not like a standard something like a standard practice. Like it can be, like you take the data and you train a model on top of it, and you get the predictions out of it. Now your domain experts come to you, and domain expert actually gives you the thing like a rating sort of, if the prediction is in accordance with the actual domain knowledge or not.
But
For example,
how do you encapsulate this domain knowledge into the
yeah.
model?
Yeah. So there are many ways. Like you can penalize, like add penalties and all. That's how you actually, like, it depends upon how you devise your algorithm, like model algorithm. For example, you can have something, you have your additional loss for the model training also, but at the same time you can also include another loss that actually says like that your if your domain knowledge expert says this thing and my model prediction is this thing, you can actually also include that loss also in your model, and your model actually trains not only on models in internal weights, but also model internal parameters, but also on the domain knowledge loss thing. So there are many various. I think there's a different thread of research also. There is this thing called human assisted machine learning, which I think if you also see in recent, I mean, obviously, everyone knows about ChatGPT and all, where you have this thing called RLHF, which is reinforcement learning based human feedback. What you do is like you write something in the chat, like a factual question, for example, and your ChatGPT gives you some response. It may not be factually correct, for example, but you have an option to say, is it the response correct or not? Yes or no. And when you click on yes, that feedback goes back to the model, and the next time it's trained on a similar sort of question, it the probability of failure is much less. So that depends upon how the you actually build the model. Like in case of language models, it's transformer based, and that's a different whole new different architecture. So that is different from just having a very simple linear regression model. So it depends model to model, and like sort of the engineering aspect of it, like how you build it and all.
Can we say that thresholds are encountered, thresholds on the values of the random variables can be interpreted as a domain expert knowledge?
Thresholds in the values, threshold in the values of what, like the prediction values, or
No, the thresholds on the random variables. On the See, when you are solving for the prediction, you are solving for the random variables, and the random variables, the can you say that this random variable cannot exceed this value, or it should be above this
okay.
value?
Okay, by random variables, I'm assuming you mean like some output random variable, right? Like for
Output,
example,
output.
yeah.
Yes, output random variable.
Okay.
You are right.
Yeah. So for example, obviously something like if you do a regression problem, and for example, you do in a medical setting, for example, you say like, given my this symptoms, my lab test, blood test value for sugar levels would be like something like, with this, it's obviously within some range, or even your blood pressure would be actually even some within some range, but your regression model can actually give you something out of range value also. And so your domain expert can actually come into the picture and say like, no, your model gives me like error prediction, like this is not correct, because normally blood pressure ranges from this to this for an average human being. And in that case, yes, like obviously a thresholding you need to keep, and that can be given by a domain expert.
And also, is it fair to say that graphical models is actually relating the random variables between the different random variables at different levels? I mean, establish the relationship between the different random variables.
Yes, graphical models actually does that. Like it's basically the way to sort of see like how different random variables in the in the problem setting actually are connected, interconnected or not. Like the correlation, for example, between two random variables. And there might be like sort of conditioning also. We'll see in in the case of Bayesian networks. There's this thing like, if a event can be a random variable. Like if event, I would say a random variable, if a random variable is conditioned on another event or something, then you have a directed edge from. So I would go through that, but the edge actually means a correlation between, or the relationship between two random variables. Yeah.
Yeah, the other question is, when you talk about joint probability distribution, there must be some way to, I mean, if you have n random variables, it is not possible that there should be a relationship between each and every random variable. So there should be a way to reduce the model also.
Yeah, obviously. You start with a like a complete graph with where you have all the random variables connected. So we would be discussing that, like it's not,
Okay, fine.
it's like not all the random variables are actually connected, so those things are there. Yeah. So we first start with an example. One is of Bayesian network, and one is of Markov network. So we saw like the hierarchical division. So a directed graph, under directed graphs we have Bayesian networks, and under undirected graphs we have Markov network. So if you see here, in case of Bayesian network, you have a directed edge between different random variables. Like you have, let's say this is the first example is from the Daphne Koller book on probabilistic graphical models. I think we had, I had actually shared a reference to it, and previously I would share it once more. So the example is as follows. Let's say you have a student, and the student wants to apply to an university, like a graduate university, and hence they require a letter of recommendation from a professor, and also has to give an SAT exam to get into the university. And so what he does is, what he or she does is, like he or she takes an exam, and the exam has some level of difficulty. So the course difficulty is given by the random variable difficulty, and the student's intelligence, although I mean, just for the sake of example, we can't quantify it, is given by this random variable here, which is intelligence. And the grade is actually sort of the course grade that the student gets, and the letter is the letter that he or she gets from the professor, and the SAT is the random variable indicating the SAT score that the student gets. So if we see the connection here, so if the course is too difficult and the student has high intelligence, and um, they those two actually indicate uh, sort of good grade. And if it indicates a good grade, the professor is likely to give you a letter of recommendation, because you got a good grade. And so from grade to letter there is a directed edge. And also if you have good intelligence, you can probably crack SAT also. And there is a directed edge from intelligence to SAT. And that's the notion of Bayesian network. So I'm just pulling out an example, which the book by Daphne Koller has. And in the case of Markov network, there is nothing such as directed edges there. So there is A, B, C, D different random variables, and uh, those are interconnected like that. So um, what is the difference here? So in the case of undirected graph, the age actually means a correlation. Like A and D, two events are correlated. Like if A also is happening, there is a good chance D also is happening. On the other hand, if D also is happening, there is a good chance A is also happening. So there is a two-way sort of um back and forth connection. But in the case of Bayesian network, um, if you if you see the grade and letter part, if you get a good grade, you would get a good letter. But if you get a good letter, doesn't mean that you got a good grade. So that's the notion. Like it's a one-way sort of flow of events in the case of Bayesian network. So there's just a high-level overview, but we will be going into much more detail. I'll see more examples on it. Um, so in the case of image segmentation that we were talking about, how do you represent it as a graphical model? So the image pixels, as I mentioned, you can think of them as the random variables or the nodes in the graph. And the nearby pixels you actually connect with an edge. So if you see the red node, it comes from the image of the cow, and so the blue nodes are actually the surrounding pixels in the image, and those are connected as part of the graph. The first example is from a diagnosis network for a medical diagnosis. Just you can actually go through the paper UAE, but it's just a motivating sort of picture that I wanted to show here. And so what, if you see the diagnosis network is too much complex, like there are so many random variables connected, interconnected, and all, and it's not even humanly interpretable. Like you can't interpret like what is the variables and all from the image, but if you feed it to a model, sort it can give you good inference like on sort of predictions. So that's the idea. And so graphical model actually provides you an intuitive and compact data structure. The other one is like you get efficient reasoning through general purpose algorithms. Also you have this sparse parameterization also, because if you have expert knowledge and all, you don't probably don't need to learn too much weight and all. And also from learning from data also can help you further. Like if you already learned a model and then you apply probabilistic graphical models on top of that, then you don't need that much parameters. So there are many applications of this. One is obviously in medical diagnosis. Second is fault diagnosis and in natural language processing, social networks, and other areas like computer vision, speech, and robotics and all. So it's a widely applicable sort of like a sort of like a building block in many fields, many applications, and that is why it's so important that we study this in detail. Because in the recent times, in case of generative AI, also this is very much employed, and sort of this is very much into picture. Like the building basic building blocks includes probabilistic graphical models. So in the case of, I think we can skip this slide. I think the same image segmentation I had included. So the other application you can think of is like a multi-sensor integration. For example, in Google Maps, for example, if you see, like when you open your Google Maps, you see things um, like if you see the destination that you're trying to reach, the path that you see on the map has different color codings. Like red means there is a traffic jam or some congestion in the road, and if it goes a slightly blue and all, there is a little congestion and all. So how do you get this data? So one obviously is, here I also include things like weather and all. This for like in case of like if the my weather is bad, like should I if I take this sort of shortcut road, does this road gets waterlogged or something due to rain and all. So those kind of information you get from different modalities of data, and you train your model and you learn, let's say, your uh, the shortest path that also has uh, very less congestion, and also other factors into account. So that's the idea. And in case of stock market also, like there are various ways also, factors also, like various random variables also takes into, like taking that keep that are there in the picture. Like random variables can be things like market crash, or other details about the market or something like that. And those are also sort of like give you like sort of um, also affect like how your stock is going to perform in the upcoming few months or something like, or in some timeline. So these are various applications. Some other applications also I want to bring up. And the other application is heavily used, I think, in text recognition part. Like let's say you have image of in like in for example, I think now there is this Google's app or something. If you like recognition, sort of image recognition part, where you click on a signboard, like you point your camera to your signboard, and it reads out like what is written there, or if it's in a different language or something. So for example, if you see this particular example, you have the like and cat, but the h, both of them have an h, but for the first word you interpret the h as h itself, but the second word you interpret h as a. So how does this thing sort of from a human side, it's fairly easy for us to actually see. But for a machine learning model, how do you sort of train your model so that if you give an image like this, it can train correctly, predict correctly what is written there. The other obviously important application is information extraction. Things like this is highly used in Google search and any other search engine. For example, in case of this sentence like Mrs. Green spoke today in New York, and Green chairs the financial committee. So green is actually a color also, and is in the second sentence, Green chairs the financial committee. Does that Green actually refer to Mrs. Green or something else? So that's a sort of like there is many ambiguity also in the sentence. Like from a human perspective, we can say like it's about the same person, but for a machine learning model, it can be if uh, along with these two sentences, if we also have other sentences that has words like green t-shirt or a green flag or something like that, then it can actually refer to that color green, not the actual person green. So those kind of ambiguity can also is also like has resolving those kind of ambiguity also is one of the ways through graphical models. And and the issue is that how do you do this? Like we spoke about inference, which is like you check from local observations, you want to make global predictions. So you have local ambiguity, but you want to make global prediction in the fact that green actually means in the entire sentence to the a particular person, not the color green. So if you just focus on local prediction, it can actually falsely um, say like it's the green color. But if you see globally over the entire sentence or like entire paragraph, it it can learn and it can predict correctly that it actually means the person. So that's the idea of inference. And so I want to give a brief overview of the sort of like how we are headed now. So first, we want to look into representation, like in the sense like how the joint distribution that we discussed, like probability of y1 to yn, how do we store that? Like how sort of like as you mentioned, as one of the participants mentioned, like all the variables may not be connected to each other. There might be slight, there might be few more nodes in the graph that are not connected. So that is one aspect. How do we store that? The other aspect is like how do you represent this directed graphical models and the undirected graphical models? What are the assumptions there? Like this, in case of undirected graphical models, we saw like the edge actually means correlation. So that's an assumption, but in many cases that's the assumption itself. So those kind of things. There are other assumptions also, like it depends upon the application. So the second part is inference, like things that we saw, like answering questions with the model, or exact or giving out an estimate, which can be exact or approximate. And the third is learning, like things like learning the parameters of the model, the structure, and what like you have various forms of data. Which model should you apply to a particular data type? That also comes from the learning aspect. So we do a recap of basics first. I think in the case of graphs, we first go through various basic concepts. I think many of you already know, but just a recap, sort of, or quick recap. So we all know like what graphs are like. So a collection of nodes, and where each of the nodes are have edges, are connected by edges, and there can be two like categories. One is undirected on the left, and directed graphs on the right. And we have special graphs also, things like trees. Trees is a special kind of graph. It's undirected, but it doesn't have any cycle. The other case is spanning tree, where you have the same set of vertices but a subset of edges. and you that's all the nodes are connected, but you again have no cycles. So on the left in the diagram, if you see, it's not a spanning tree, but on the right it's a spanning tree of the original graph with all the nodes connected, but none of them have a cycle. So we now come to the concept of directed acyclic graphs, or DAGs for short. And what what do they mean, like in terms of DAGs? So if you see the word acyclic, on the right hand side, you I have actually grayed out the node E here. If you see, like, you go from B to C by via the directed edge, then you could have gone from C to E via C to E edge. Then you could have gone from E to B. So you are back to B. So it's a directed cyclic loop, sort of. But in case of directed acyclic graphs, because it includes the word acyclic, so there can't be any directed cyclic loops in the graph. So all those directed graphs that doesn't have a cyclic directed path are actually called directed acyclic graphs. So we would be using this thing later on in Bayesian networks, this particular property. And so in terms of probability also, I think we already have done a probability basic course, like sort of like basic lecture, but just a high level again. So what does P of A mean? Like, it's from a frequentist point of view. If n is my total possible sort of trials, and if I set n to infinity, so the number of times my a is true divided by n is actually, in a continuous setting, is a probabilistic interpretation. So in there are two views, like probably one is frequentist view, one is Bayesian view. The In case of Bayesian view, is basically means P of A basically means your belief about A. So we sort of had this Bayesian view in case of priors, in if you remember, in linear regression, where you have this prior beliefs, like you could have made an assumption on the prior, that it comes from a beta distribution, for example, or a normal distribution. So these are actually called beliefs, and that's a Bayesian view point of view. So now we sort of go back to the example of that student example, where we had the intelligence difficulty of the course and grade of the course, and we now try to define the joint distribution. What do we mean by that? So the joint distribution of P of I comma D comma G, so I D G are actually the random variables here, is basically, I actually have given, like, this is again an image from the Daphne Koller book, where they have provided some like numbers here, like obviously, these are just an example from a data they have in the book. So probability of I equal to I0, comma D equal to D0, comma G equal to G1 is equal to 0.126. The joint probability of I0, D0, and G1 is 0.126, and so on. And now, what are the independent parameters here? Like, parameters, like, what do you mean by that? Independent parameters is basically like, is my I, the intelligence and the difficulty, are they independent, or are they dependent? Are they like independent events, or are they dependent events? So those are kind of questions we want to answer. And how do we do that? One is like, you can condition on G1. For example, the condition on G1, so G1 is on my first row here, and G1 again is on I think on fourth row, and so on. So you condition on G1, and you keep G1 fixed, and you check I and D rows, and you check, like, are those values sort of like, in some sense, if I0 is very high, like, if I0 and D0, is there some pattern in that, like, if you condition or fix G1. So that's the idea. um, and so um, what do we mean with conditioning? So in terms of, from a Bayesian view, we mean like, what do you believe about capital Y, the event is equal to Y when I tell you about the event X. So an example can be like what is the probability of France wins Euro 2020? It's not a conditional, but if I give you preconditions like things like France has won the World Cup in 2018, and they haven't had any catastrophic results since. So can you predict like they win in Euro 2020? So I picked up a this one from one of the slides of another course on Professor Batra, and the dates are I think a little bit later previous. So this these are actually one example. So again like I now what I did is I actually removed all the rows here. I only kept G1 as the conditioning thing, and so I kept G1 as fixed. Now I observe I0 and D0 here, and I try to see if there is any pattern here. And if there is no pattern, that means like the events I and D are actually independent. And that's the idea. And we what we do again like is this just a normalization part, our sort of like this an unnormalized measure on the left hand side, and I do a normal when I do a conditioning sort of, which is P of ID given G1. It's you're actually what this actually means like P of ID G1 by P of G1. So that's a normalization in that sense. The my values also change due to that. And so another example can be like P of G given ID, where I fix ID to different values of I0, D0, I0, D1, and so on. And I check for each of G1, G2, and G3 what's the sort of values there. And you fix I equal to I0, D equal to D0, and I equal to I0, D equal to D1, and you check for all possible values of four combinations, 2 to the power 2 combinations, and you check what is the value of G here. So obviously like this is just a sort of basic recap which I'm doing here. So by base rule, obviously you know like this is the thing. So in case of if of for a joint distribution where you have x y and your vertical axis as the z thing, what do you mean by p of x comma y given z? That means actually like you fix z here is actually a particular value like z equal to, let's say, small z or something, and you fix that particular vertical axis to one specific um, sort of like a rectangular box, and for that you actually pick up all combinations of x and y. So that's the visual notion of condition probability distribution here. And um, similarly here also so the other concept also now comes is marginalization. So we discussed conditioning. Now we want to discuss some marginalization. So let's say I start with probability of I comma D here as follows. This joint probability between uh, I and D, and we are given this probability. Now what I want to do is like I want to just calculate for uh, create this table of only D for D0 and D1, because D only has two possible values, D0 and D1. And what is the probability for that? So if you see here, what I did is as follows. For D0, I have in the first row and the third row, I sort of sum it up like 0.564 plus 0.282, I get 0.8846. And for D1, sum 0.02 and 0.134, I get 0.154. So marginalizing I actually means is that for D0 I am actually summing I0 and I1 values, and for D1 also I am summing up I0 and I1 values. So for the marginalized I is actually summation over all possible values of I over this joint probability distribution. And so things like, obviously, like, if you remember, like events, like you can represent your probability of a, like let's say you have two events A and B, and so you can represent probability of A as probability of A and B and plus probability of A not B. Similarly for random variables, this is again the concept of marginalization that I'm bringing up. um, so one was for events. You can represent marginalization as follows. For random variables, as you saw in this example, you if you want to calculate for one particular um, random variable x here, you marginalize over all the other random variables y equal to y. So that means you sum up for all the other random variables y equal to y. So again, block diagram that I'm showing here, the same thing from the previous slide we saw. And uh, so there is a two-step marginalization. First, I marginalize over the entire z-axis, and so I get from probability of x comma y comma z, I get probability of x comma y. So from a 3D structure, now I get to a 2D structure, and now I just want probability of x only. So I again marginalize with respect to y, um, and I get a 1D sort of uh, uh, probability of x only. So now we come up with the concept of factors, which we saw in the hierarchical diagram picture for undirected graphical models. Um, so in case of, let's say I have k random variables. I define a function phi of y1 up till yk, where phi, you can think of it as a function, and so that function actually gives me a real numbered value. And the scope, what do you mean by scope? Scope actually means the domain of the thing, like it actually domain of the function. So a function of y1 to yk basically means a function of the random variables. I define one such that it gives me a real valued output, real numbered output. So in the same example, probability of the joint probability of dij as follows. I what I have is, if I condition on, if I just take g1 only as follows. What is the scope here? In the case of this particular example, I have, like, can you answer, like, first, like, what is the scope here? Like, anyone, like, so in this case, because I'm only picking one sort of, I already fixed g1. That means I only am left with d and I only. And so d and I would be my scope here, because those are the random variables that I um, can sort of change, and the factor here, the function, can be thought of the probability. So the probability is actually a real valued output, because it falls between 0 and 1, and that can be thought of as a function. And since I already fixed g to g1, I am only left with d and I, which I can again tune. Sort of, d can take two values, d0 and d1. I can take two values, I0 and I1, and that's the those are the only two like scope, like falls another scope. So another way is, this phi, this function phi, uh, may not be only in the case of probabilities. So the probability obviously is a function. If you can think of it as a function, because it outputs a value between 0 and 1. But it can be also other notions of defining a function. So let's say I have two events, two random variables a and b, and each of them, a takes a0 and a1 as values, b takes b0 and b1 as values, and the function phi can take any real value. Like, let's say a0 and b0 together, phi of a0 and b0 together is actually 30. It's not a probability because it doesn't fall between 0 and 1. So there are different notions of there might be general function or general factors, and that again depends upon the problem or the application in hand. If you want a setting where you want to predict, for example, probability, then you have a probabilistic function. But there might be settings like stock prediction or something like that, where you actually want to have like real valued numbers, like what is the stock price, what would be the stock price after this time period and all. So those are real value numbers and those are not probabilities, and in that case you can have something like a general factor depending on the application that you are working on. So now, similar to probability, like we have something called factor product. It's fairly simple. If you see, let's say, so this individual thing is a one single factor. So this thing is actually, we call it, this entire matrix you see is a factor. So on the right hand side, on the left hand side, you have uh, a, like for event a and b, you have a1 b1 a1 b2 and so on, and you have the corresponding um, probability. So here we are considering probability as my factor function. And for here in the middle part, I have factor for events b and c, and I again have like probability values for them. I now want to multiply them to get the joint sort of distribution, like probability of a comma b comma c. I now only have probability of a comma b, and here I have probability of b comma c, but eventually I want probability of a comma b comma c. So how do we do that? So if you see here, it's very similar to matrix product. If you So the intuition is very similar to that. So a1 b1, and I multiply a1 b1 and b1 c1. So that basically means the middle element b1 here is common here. Similarly, a2 b1 and b1 c1 we multiply, and what we get here is like for a1 b1 c1, I actually multiply zero point 0.5 and zero point 0.5 as 0.25, and for a1 b1 and c2 I multiply, I take the first row a1 b1 zero point 0.5, and since I have b1 c2 here, I take the second row of this table b1 c2, and I multiply zero point 0.5 and zero point 0.7, which I get 0.35, and I complete the table as follows. So there is a very similarity with the matrix multiplication also. If you see, why? Because let's say you have three matrices, x y z. X is of dimension m cross n, y is of dimension n cross p, and z is of dimension p cross q. So if you want to multiply, so the product xy actually exists because it's of dimension m cross n into n cross p, which is m cross p. So xy is of dimension m cross p, and you now have another matrix z, which is of dimension p cross q. You can again multiply those. So the middle dimension is always constant for when you are multiplying two matrices. Similarly, here also, when you are multiplying two factor tables, uh, the corresponding variable that you are trying to join has to be the same. um, um, and again, you can also go back, sort of like, this is a forward sort of, you can think of it as like a forward thing. Like you have two tables, a for event a and b and b and c, and you try to calculate the joint distribution. Now from the joint distribution you can also do a marginalization. Let's say I just want to remove all b's here, and I just want to, so let's say I have probability of a comma b comma c, and I just want to get probability of a comma c. And so the same way we did marginalization, where we sum it up over all the other random variables. In this case, we sum it up over all values of the random variable b. We get the final output as follows. So before we head on, is there any particular doubts or questions? So let me know that. Okay. I think. Um, So we can do one thing. I think we also have to revisit part of the bias variance trade-off from yesterday's lecture. We can take that up now. We can continue in next week from this part of factor reduction, and then on I think we can actually continue into this part, or maybe I can do a slide of lecture on Bayesian networks now, and then I can finish this lecture on bias variance trade-off, and next week onwards we can continue on this slide. Yeah. So I think it's time is I think 4:32. We still have 30 minutes around. So let's discuss on a high level what's Bayesian networks. Um, Bayesian networks are basically DAGs, or directed acyclic graphs, as I mentioned. So they have the property that the so it's a basically a directed graph, but they shouldn't have any directed cyclic paths. And in the what does the nodes represent? The nodes in the graph represent actually variables in the probabilistic or Bayesian sense, and edges represent conditional dependencies. Note the word conditional dependencies. In the case of undirected graphs, we mentioned that the edges actually represent correlation between variables, but here it's actually conditional dependencies. So there's a difference. So one example can be like, suppose say the flu causes sinus inflammation. So flu is actually a node in the graph, and sinus inflammation is also another node in the graph. And since flu causes sinus inflammation, you have a directed edge from flu to sinus inflammation. Similarly, allergies cause sinus inflammation. You have a directed edge from allergies to sinus inflammation. And sinus inflammation, on the other hand, causes a runny nose. So runny nose is your random variable, another random variable, and there is a directed edge from sinus inflammation node to the node runny nose, and similarly so on. So these are all connected like that. So if you see the image now here, so flu to sinus, allergy to sinus also, and sinus actually gives to running nose and headache. This is your Bayesian network structure, sort of the graphical structure. And in the case of how do we represent it as a probabilistic way? So we have a set of random variables. Obviously, it is a DAG, because it's a directed acyclic graph, and it encodes independence assumption. That means like the edges actually means, if there is an edge, that actually means they are conditionally dependent, and if there is no edge, that means they are conditionally independent. So it encodes independence assumptions. And it's also another way to see as like, since this is a sort of like a tree structure, not, it doesn't have any cycles, it is a tree. So it's a conditional probability tree. And also you sort of get the joint distribution also, as follows: like probability of y1 to yn is actually a product of yi given pa of y. So pa of y actually means the parents of y. So if I come back to this example, probability of flu comma sinus comma allergy comma headache comma nose is equal to probability of flu into probability of sinus given flu and allergy, because parents of sinus are actually flu and allergy. And so I have probability of flu into probability of sinus given flu and allergy into probability of headache given sinus, because sinus is again a parent of headache, into probability of nose given sinus, because sinus again is a parent of nose. So if you see this is the basic sort of formula here. So you um, you have the probability of yi given sort of p of a y, or the parents of the random variable yi. And in case of like how many parameters there do you have here? So you have discrete variables like y1 to yn, and your graph defines the parents of yi as probability of a, like pa yi, and the conditional probability trees or cpts for short are actually p of yi given p of ay, parents of yi. So I won't go into Markov-ness for this lecture. I think I have given a very high-level overview of Bayesian networks, but we would be diving more deep into it in the next lecture. And I think for the remaining part, I can take up. So before I can take up yesterday's part on bias variance trade-off, and before we head on, I would like to know if there is any other questions. And Yeah, feel free to speak up if there are any questions you have. There's a good opportunity. I think we would be having um, the bias variance trade-off. I think that would take a good amount of uh, 20-30 minutes time. Yeah. Okay, I think. Okay, I think there are no questions. So let me reshare my screen once again.
Sir, once again, please explain. Hello.
Yeah.
Once again, please explain that direct acyclic graph and direct graph. Please,
Okay.
I want
Okay.
to clear.
Yeah.
I want to clear that.
Okay. Okay. Yeah. Sure. Let me open that. Um,
Explain with an example. In that there is only A, B, C. I want
oh, okay, okay.
I want
Yeah.
some example so that I can have clear cut
Okay.
idea.
Let me draw it out so that it's easy. I hope you're able to see, right?
Yes, yes,
My
clear, clear. Eh,
okay. So, in case of a directed graph, you have something like this, like you have nodes and all. So you can draw any sort of edges like this, um, and let's say I have now, instead of this thing, I have something like this. Like, let's reverse the edges. So let's say I have something like this.
Okay,
So this is a directed graph because all the nodes are actually connected via directed edges. Um, but it's not a DAG or a directed acyclic graph. Why? Because if you see, like, let's label these nodes A, B, C, D. So you can go from A to B. You can think of like hopping from a node to node. Like, you can hop from node A to node B. You can go from B to C. You can go from C to D, and then you can again go back to A. So there's a loop here.
okay.
But DAGs actually is called directed um, acyclic graph. So that means obviously it's directed, but it has a word acyclic. Acyclic loop actually is a cycle. That means a cycle itself. But
Okay.
acyclic is actually without a cycle. So without a cycle is acyclic.
So all the Bayesian networks are DAGs.
All the Bayesian networks are DAGs. Yeah, they don't have a cycle like this.
Okay. What is the benefit here?
So the benefit, I think, like would be much more clear in the upcoming lectures. The one is like we already what we are encoding is basically the conditional independencies here via the edges. So that means, let's say I have a simple example of a DAG. Let's say I have this. So this is a edge, and this is a edge. So these are cyclic graph. This is not a DAG. So we saw like the edges represent the conditional events, conditional dependencies between the random variables a and b. So let's say I didn't have this edge. So that means a causes b. So in the case of, let's say, if I go back to the example here, flu and sinus thing.
Yes,
Let's
yes.
say I see stick here only. A causes B, so A can be flu and B can be sinus. Um, but if I also have a edge like this from B to A, that's a weird thing because sinus inflammation doesn't cause flu.
Hmm.
It's the other way around. So that's why your Bayesian network cannot have a cycle in that sense. That's the requirement. I
Okay.
hope that's clear. Yeah.
Yeah, clear, clear.
Yeah. All right.
Thank you.
So I think we can start with the yesterday's lecture on um, mm, it's a lecture on bias variance trade-off. So we sort of saw yesterday. So I'm gonna start a little bit. I think we already discussed these things. Like if you increase the model complexity, your prediction error or the training error goes low as possible. But at some point, your test error first keeps on decreasing, but it starts on increasing. So if you see on the left hand side, if I have drawn a simple model like a linear sort of like a example, but on the right hand side it tries to fit on all the data points like a curved polynomial. So in that case, my test error starts to increase, and that's the classic case of overfitting, where my model is so complex that given a new test setup, I cannot sort of predict. I don't get a good test accuracy. So we discussed three main sources of test error. One is bias, one is variance and noise, and we sort of like saw like let's say I have the true function um, as follows. The true function is a curved line where each of the data points, like this circles are actually my data points, and I try to fit a curve through it, which is the true function, and the straight line is my fitted hypothesis or the prediction, one of the estimators you can say. And so y here is actually my true function, and fx is actually my fitted hypothesis, plus some epsilon, that is the error that I get, like the difference between the true function and the fitted hypothesis. And there can be many ways to fit a line, so I can actually fit 50 lines, for example. Given this true function, I can fit many multiple lines. And so what is a good estimator? Like there can be many possible fitting predictor lines. So I define the bias as follows. So from from the example that you see, that there are 50 lines here, I take up one out of them, which is actually the average of all the 50 lines, and I say like that's the my mean prediction. The mean prediction line actually falls in somewhere in the middle, like here, and and I also have the true function. So the notion of bias is that how much does the average of gx is actually the predictor, like all the functions, all the 50 lines are actually represented by gx. Each of the lines are represented by gx. So it can be g1 of x for one line, g2 of x for another line, g3 of x for another line, so on. So I'm denoting it as gx. So the average of all gx, which is the mean prediction, I denote it as g bar x, differ from fx, which is the true function. So I think I made a slight notation here. So fx is actually my true function, and I add, which is the curved line here, and I add a noise to it, and my adding the noise actually gives me the fitted hypothesis, because uh, the true function and the hypothesis are actually not coinciding. They have some gaps within them. In this case, like you have a gap here. In this case, you have a gap here. So that epsilon actually captures those gaps. So that's the notion of bias is basically how much does my true function differ from the average of gx or g bar x? So I do it as follows, like g bar x minus fx. And the case of variance is like how much does g of x, one of the estimator, or the predicted fitted line, vary on changing the underlying training set. That means how does g of x uh, deviate from the mean prediction g bar x. And if you know, this expression is actually the variance expression. E of x minus e e expectation of x whole square is actually the variance of x. So in this case, it's a variance of the estimator, variance of g of x. And there is another thing called noise, which is the unavoidable error. We saw like y equal to fx plus epsilon. This epsilon is actually the noise. So the noise doesn't depend upon the model choices. It can be from the observation and all other aspects. So what we do is we in the last part of the lecture yesterday, we did a bias variance analysis in the regression setting. So let's say my true underlying function here is as follows: y equal to fx plus epsilon, where epsilon is a noise coming from the normal distribution with mean 0 and variance sigma squared. And um, say like the true underlying function, yeah, so let's say I have a data set of n samples, and d is equal to xi yi, where ranges from 1 to n, and we fit a linear hypothesis. So a linear line, which is parameterized by w, is similar to the linear regression setting, because that's the thing that we are trying to analyze. So you can think of gdx or g of x for simplicity as w transpose x, um, which is used to minimize the sum of squared errors, which is the least squared error, which is yi minus gdxi whole square. So yi is my actually the ground truth labels, and gdxi is my prediction, the linear hypothesis that I want to fit, and I calculate the sum of squared errors. So now what I do is I get a new test point x hat, whose corresponding y hat would be equal to f of x hat plus y epsilon hat. Epsilon hat and epsilon you can think of it in the same, but I just added a hat here just for showing. It's only this thing that changes. So what I want to do is I want to find out what is the expected test error on an x hat. That is this error of x hat, uh, which is equal to expectation of over d and epsilon hat of gd x hat minus y hat whole square. So that means the loss function, the squared loss that we see here, in the case of test set, what is the expectation of it? How does the predictor, the linear hypothesis, vary from the ground truth uh, y hat uh, on the whole square of it, because it's a sum of squared errors. For the sake of brevity, we will use just a expectation e instead of expectation this complicated notation here, and we use g of x only instead of gdx. Um, and what we wanted to find out is this error, this thing, the expected test error, gdx hat, y hat. We wanted to sort of decompose this to find out some insights. So, like, um, what does it have? Like, so what we do is we get expectation of g of x hat minus y hat whole square. We expand it. So we open the square expression with a square plus b square minus 2ab, and we get this. And since you know, like, expectations are linear, like expectation of two sum of two variables is actually sum of the expectation of x plus y is equal to expectation of x plus expectation of y. So that's why the individual variables comes out like this. And now what do I do is I pick up this first expression, expectation of g of x at whole square, and I can write it as this, because if you know, variance of x is equal to expectation of x square minus expectation of x whole square. And so expectation of x square, if I take this thing on the right hand side, would be basically variance of x plus expectation of x whole square. Instead of x here, now I have g of x hat, and in the same way, just replacing that, I can just get epsilon expectation of g of x hat whole square as follows. So this is a variance of g of x hat, and this is the expectation of g of x hat whole square. So g bar x hat whole square. It comes from the definition of variance. And I replace this thing here, and I keep the other things as same thing as before. And we apply the same, like what we do now is, like for what we had was epsilon y hat whole square minus 2 into epsilon g of x hat into epsilon y hat. For this epsilon y hat whole square, this particular expression, we again do the same thing. We apply the same trick using equation 1. We write expression of y hat whole square is equal to the variance of y hat plus the mean of y hat whole square. And for this thing, like we want to, again, like we want to find out what is the expectation of y hat. We What we do is, we know like y hat is equal to f of x hat plus epsilon hat. So we expand that as follows. And this is again a linear sort of, it can be broken down linearly. That's expectation of f of x hat plus expectation of epsilon hat. Now, if you remember, epsilon hat actually comes from this distribution of mean 0 and variance sigma square. So the mean is 0. As a result, my expectation of epsilon hat would actually comes out to be 0. And I'm just only left with expectation of f of x hat. And since f of x hat is a constant, in this case, it comes out as only f of x hat. And what I do now is actually I replace e of y hat by f of x hat, and I get this following expression as follows. And if I see now, like g bar x hat whole square, f of x hat whole square, the things that I've circled out here, minus 2 g bar x hat into f of x hat, this thing is actually a squared formula, g bar x hat minus f of x hat whole square. And I now get a much more simplified version as follows. um, I get, so the I initially started out with this expectation of g of x hat minus y hat whole square equal to, what I get now is as follows. Sum of three terms. If you see clearly, the first term is actually the variance of g of x hat, which I have written here. The second term is actually the the bias here, because it's how we define bias as how the true function deviates from the mean prediction. So the second term is my bias of g of x hat. Now I have a whole square also on top of it, so I have bias of g of x hat whole square. And the last expression is y hat minus f of x hat. If you remember, y hat was equal to f of x hat plus epsilon hat. So y hat minus f of x hat would be just epsilon hat, and this thing would just be expectation of epsilon hat whole square, because I have a whole square here. And epsilon hat, if you know, like again using the same trick, I get like same trick as this thing. Variance of expectation of x square is equal to variance of x plus expectation of x. Instead of x, now I have epsilon. So expectation of epsilon square would be variance of epsilon plus expectation of epsilon whole square. So since epsilon comes from normal distribution of mean 0 and variance sigma square, the expectation of epsilon would actually be just 0 because my mean is 0, and variance of epsilon would be sigma square because the variance of the normal distribution is sigma square. As a result, I get expectation of epsilon hat whole square is equal to sigma square. So that's the notion that I wanted to share here. What we get as follows: expectation of g of x hat minus y hat whole square is equal to the variance of g of x hat plus bias whole square plus sigma square. So that's the thing. So I think I'll just give a concluding remark on each of the measurement, each of the notions that we discussed. One was bias, which means the difference between the true function f of x hat and the average of g of x hat, which is the mean prediction. The variance was actually the variance of g of x hat across different training data sets. Uh, that means like for different training data sets, I get a different estimator or different linear hypothesis. I want to check how does that deviate from the mean prediction. And I lastly have a noise, which is a irreducible noise, which is the epsilon expression of epsilon whole square, which is the sigma square, because it comes from a normal distribution of mean 0 and sigma square. So I think that's where we would be ending bias variance trade-off. And I think um, um, only the last slide would be this is the case of overfitting, where the proposed hypothesis uh, fits the training data too well. You train your model on the training data and you get a high training accuracy. But in the case of new test data, it doesn't do well. So in that case, what you see is like you have high variance, like high complexity. Basically means like the model is very complex, and that means you have high overfitting. And high complexity actually indicates high variance and low bias. So that's one takeaway from here. And I think that's where we would end for bias variance trade-off, and also for this lecture also. And so any questions specific to this, like before we end our lecture today? And okay, I think
Sir, we in future classes, do we discuss Monte Carlo simulations?
uh, I no, I think we would have Monte Carlo. I think MCMC sampling is there. Monte Carlo sampling.
Acha.
Um, okay, so we would be having that in some um, in later phases, like in some, I think next to next week probably.
Okay,
Um,
okay.
yeah,
No, we are studying, na?
yeah, yeah.
Okay. Thank you.
Yeah. So I think for this lecture, I think for the next set of lecture, we would be continuing on the factor reduction and the uh, deep dive into the Bayesian networks and Markov networks.
Okay.
And yeah, so that's the idea. So
Fine.
any other questions? Like,
Sorry, another one I want to ask in the DAGs in the Bayesian networks. Can we? I want to clear a Markov blanket.
mhm.
Do we? That means how does it is been uh, inferred with the networks?
um, I think we would be covering Markov blanket next week probably. Maybe I think we can discuss that at that point because other
Okay.
audiences may not be.
Okay.
Uh,
Okay.
yeah, sure.
I'm having doubt in that one. Fine. Fine.
Okay, okay. Or you
Fine.
can reach out to me separately on email. Maybe also I can
Okay, sir.
take that.
Okay, sir.
Yeah,
Okay, sir. Thank you, sir.
yeah,
Thank you.
yeah. Yeah, so for the next few weeks, I think we will be discussing on the Markov nets and all. And yeah, I think that's it. Any other things? And also, I think I had previously mentioned about some about one was about the course certification part. So I'm still like waiting on for the course moderators from ISC and all for giving me more sort of like the template and all and more details on it. I will share with you in the upcoming week for that. And also other thing was about quizzes. If we would be having a quiz or something next week. I'm not too sure at the moment, but I will keep you updated over email if there is something like a quiz or something that we would be having. And these are not graded quiz, so these are probably ungraded, but uh, this would count a bit towards your course certification. So I would get about like I would check into more details once I have from their side also. So yeah, and the I think that's more or less it. I think I don't have any other things to
So one
say.
thing, sir, can you focus on the wireless in wireless communications? How the probabilistic models can be incorporated in wireless signal processing?
Um, Actually, I don't have good knowledge about wireless networks because I'm not from like sort of that background.
Okay.
Probably I can share some references with you, like sort of, but I'm not too sure like how um, on a deeper level like how you can apply that there. Because in this course I think although we would be discussing applications side by side, but would be mainly the concepts and all.
Yeah, yeah.
So
Fine.
yeah, so I will check like if I can find some
Okay,
references.
sir. Okay, sir. I will personally I will connect with you, sir. Thank you, sir.
Sure, sure.
Okay. Thank you.
Okay.
Thank you, sir. Thank you.
Yeah, I think we can call it off for today, and we can meet again next week. And so, one question before you all leave is that for Saturday, I think we have the class timings from 5:30 to 7. So, few other students also like had reached out to me personally saying like the previous class timings, which was from 3:30 to 5, was more suitable because to some reasons they have like multiple reasons they had, and that's the reason why we had not good attendance yesterday also. So do you folks feel like we switch to previous class timings like 3:30 to 5 same as now for Saturday? Any
Uh,
suggestions?
I have a problem, sir. 3:30. I am working on Saturday,
Okay,
so
okay, okay. Oh, I see.
uh, get back nearly it will be 4:15.
Okay, okay. So 4:30 probably, is it possible for 4:30 or something?
Yeah,
Or
I've seen most of the times. Sometimes if in the traffic I get delayed,
I see. Okay,
then
okay. Makes sense. Yeah, yeah.
so
Okay.
have some cushion timing is better.
Yeah, yeah, makes sense. Okay. Okay, I think then we can stick with the same. So anyone else like who has other opinions about the timings for Saturday? Um, okay, I think we can end this today. And if you have any questions, something like regarding the class timings, like if you want to still like get back to the previous 3:30 and all, you can just reach out to me on email or something. I will check like what can be done. Like probably we would be sticking with the same evening time, but if a lot of students actually persist, I think I have also need to check at that time.
Okay, sir.
Yeah, yeah. Okay. Thank you again for joining today, and I will see you again like next week, and we'll keep you updated in email over the week. Yeah.
Okay, sir. Thank you, sir.
Thanks again.